Okay, we're going to start our videos for Math 31, and our first unit is on limits. But before we get to the limits, we're going to do a little bit of review of Math 20 and Math 30 concepts that are going to be used for limits and also for later on in the course. So our first video here is going to be on working with inequalities and writing the solutions in interval notation and understanding how those mean. So we're going to look at a few different types of functions and just kind of quick review interval notation and how to do test points when we're dealing with inequalities. So our first thing is we're going to quickly review interval notation. So remember, when we're seeing the old way of writing things, we're looking at seeing something written as x is between -2 and 2. Remember, we would write that as in interval notation, we write it as square brackets from -2 up to +2 square brackets once again. So when we have square brackets on each end, what we're saying is that interval is closed. So when both are square brackets, we call it a closed interval. And remember, in terms of a number line, we would represent that as a solid dot at either end. So solid dot at -4, solid dot at +6, and the interval would be in between those two. So we're looking at all of the rational values between -6 or -4 and +6, and everything in between there, including decimals, fractions, roots, anything like that. So when we have open intervals, it works the same, except remember, now we don't have solid endpoints on those domain values. So in this case, our -5, 7 is an open interval, and the only way we indicate that being different in terms of a number line is open dot at -5, still a solid dot at +7, and we're doing everything in between the two once again. So it works exactly the same, just the round bracket, remember, is for an open interval. And if we only have one value and we want something like x is greater than -2, greater than or equal to -2 in this case, that's still considered an open bracket because the one end is solid, but it does go on forever in the other direction. So in this case, we would just do it as a solid dot at -2 and everything to the right, or larger than the -2. So when we're dealing with more than one interval, so often we'll do between two numbers like we just looked at, or just greater than or less than a single number, but we also get scenarios where we get dealing with two intervals. So in this case, our interval was less than 2, so if we were to put that on a number line, we'd have open dot going to the left of 2, and then we also have greater than or equal to 4, so that would be solid dot going to the right, or greater than 4. So that's our way of drawing it on a number line. We write it in the old way of less than 2, greater than 4, but in interval notation, remember, we have to sort of say, well, we're going from -infinity up to 2, so that's our open interval on both ends, and then we'd say from +4 is square brackets, since that was included, up to +infinity in the other direction. We always put round brackets on infinity because they're open and we'll never get there. And if we have two separate intervals, we use the union notation, which looks sort of like a capital U, and that's what connects our two separate intervals together. And we could do 2 intervals, 3 intervals, whatever. It really makes no difference. You just as soon as you have more than one, you just do the union notation. Okay, so this last example shows from -infinity to -1, union 1 to 4. So that would look, let's see, so I can move this up a little bit. So that would look like on our number line, we would have from -infinity to -1, so that's going to be open dot going to the left, and then we'd have from 1 to 4, and this is open dot at 1, closed dot at 4, and everything between those two. So in this case, we have two separate intervals, and we use the union notation to indicate that. So what we're going to look at today, and this is where the Math 20 review kind of comes into play, is how can we use interval notation to help us with inequality type equations. So we're going to look at rational equations, absolute values, factoring, quadratics, that kind of thing. So with an inequality like this one that's on, it's a little bit tougher because we have a fraction inequality, so we have to be aware of our non-permissible values. So the first thing we know in this question is x can't equal 5. So we have to treat that 5 as one of our test points, or one of our key numbers on the interval. The rest of the equation we just want to try to solve algebraically. So if we were to bring that x minus 5 up and multiply it out, right, we multiply the x minus 5 on both sides, it would cancel on the left. Oops, my pen isn't working so good. So we'd have our x minus 5 on the left, and then we could simplify that, so we'd end up getting 2x plus 1 on the right, on the left side, and that would be less than 3x minus 15 if we FOIL it out. We don't need to necessarily worry so much about whether it's less than or greater than. That'll kind of show up automatically. So if we take this equation and let's simplify it, let's solve it. So we bring the 2x over, and let's bring the 15 over at the same time. We end up getting 16 is less than x. Okay, so what we're dealing with in this case is we have sort of two key interval numbers. We got that 5 that we found from our non-permissible, and then we get a 16 when we solve the equation. So what we want to do is test the intervals on either side of these key points. So we have our two test points now, so what we want to do is figure these out, and it's nice to draw a number line. We know that we have something going on at 5, and we know we have something going on at 16. From the question, in the question we have just less than, so we're going to have open dot at both of those. If it was less than or equal to, then it'd be closed dot at the 16 but not at the 5 because it's non-permissible. We'll look at that scenario a bit later. And now we just want to test those intervals. So the one on the right, when we know that x is greater than 16, it actually works out that it will be greater than 16. But even if we weren't sure of that, we could just do a test point. So let's try, if we plug in something like an 18 or 17, let's try 18. So we plug in 18, we get 2 times 18, which is 36, plus 1 would be 37. And then on the bottom we'd have 18 minus 5, which is 13. And the question is 37 over 13 going to be less than 3? And it is, because 39 over 13 would be exactly 3. So that one, that interval is good. We're going to get from 16 to infinity, open brackets on both. And what we just got to be careful of, it's not only that interval. Because we have this non-permissible of 5, we're going to have some other values that are going to be possible. So just by looking at it, typically we get intervals that either go towards each other or go away from each other. So I'm just going to guess that our interval is going to be less than 5. So let's do a test point with a number less than 5, and let's use 0. 0 is the easiest one. So if we plug 0 in our original equation, we would get 1 over negative 5. Is negative 1/5 less than 3? Yes, it is. So that should work. So we should have our second interval as negative infinity up to 5, and round brackets for both of those as well. And we just finish it off by doing union of those two. And if you wanted to double check, we could try just an interval in the middle just to make sure that it doesn't work. So let's try something like a 7. So if we plug 7 in the original, we would get 15 over 2. And 15 divided by 2 is 7.5. That is not less than 3. So that one definitely does not work. So it looks like we've got our correct solution. So when you get rationals, you just got to remember that non-permissible on the bottom, and it doesn't matter whether it's a point of discontinuity or an asymptote line or whatever in terms of the graph, we just have to include that as one of our interval numbers to try to figure out whether it's going to be less than or greater than 4. So let's try another type of equation. So let's look at absolute values. And if you remember from Math 20, absolute value equations are a little tricky because we have to be aware of that those equations could be either positive or negative, because if I gave you absolute value of negative 5, that turns to positive 5 as well. So the simplest way to test these or to solve these is basically just treat each absolute value as a regular bracket. So you want to solve it first as just x minus 4 is less than 1. But then we also have to be able to deal with that as if this ended up being negative. So if we just keep it as regular brackets but put a negative out front, and then we want to solve that scenario as well. So in this case, the first one, if we just bring the 4 over, we would get, add 4 to both sides, we would get x is less than 5. For the second case, let's subtract, or let's FOIL out the brackets first, so let's make it minus x plus 4. And let's bring the 4 over to the other side, which would give us negative 3. So we should have minus x is less than negative 3. And we just got to be careful. There's a rule, if you remember, when we do dividing by like negative 1, that flips the interval sign. So instead of less than, it's now going to be greater than. So we should have less than 5 and greater than 3. So let's plot that out on a number line, and we'll do a quick test on it. So we have greater than 3, open dot, less than 5, open dot, and they should go between the two of them. So our final solution should just be round bracket 3 to 5, round bracket once again. Okay? So before we move on, let's just quickly test this. So let's try something on the left like a 0. If we put 0 in, we would get 0 minus 4, which is negative 4. Absolute value of that would be positive 4. That's not less than 1, so that definitely doesn't work. If we try something a little bigger like 6, we would get absolute value 6 minus 4, which is 2. 2 is not less than 1, so that one doesn't work. Let's just do a quick test of a 4 in the middle. Put a 4 in. 4 minus 4 is 0. 0 is less than 1. That's true, so that's good. Our interval between 3 and 5 looks like indeed it is correct. Okay, let's do a couple questions now where we're dealing with quadratics. So in this case we have a quadratic inequality, and again in Math 20 we graph these and solve these and all that, but we're not going to worry so much about the graph. Let's just see if we can figure out where these intervals are going to exist and which way they would go. So the easiest thing to do with any kind of quadratic is just factor it. Make sure it's equal to 0 and factor it like you normally would. So in this case we'd have two numbers multiply to 12 and add up to negative 8. So let's go negative 6 and negative 2. So x minus 6 and x minus 2. We don't have to worry about whether they're greater than or equal to 0. We can just sort of treat it as if it was equal to 0. So then our solutions would be positive 6 and positive 2. So if it was equal to 0, that's our two answers, we're done. But because it's a inequality, one's going to be less than or equal to 6 or greater than or equal to 6, the other one's going to be less than or equal to 2 or greater than or equal to 2. So the best way to try to test it to see which way it's going to go, let's go back to our number line and let's just try a couple of test points. So if we put in, we know because it's equal to, let's kind of start with that, because it's equal to, they will be solid dots on both. So now we just have to figure out which way the interval is going to go. So let's test a 0. I like using zeros because it's the simplest. So if we plug 0 in the equation, we get 0 minus 0 plus 12. So is 12 greater than or equal to 0? Yes. So therefore 0 works. 0 would be about here on the number line. So that means we should be going less than or equal to 2. And using the same logic, it should be, the reverse should be greater than 6. So we could test that as well. If you try something like a 7, you'll get 49 minus 56, which is negative 7 plus 12. So that does work. And if you wanted to test one in the middle, let's try 3. You'd have 9 minus 24 plus 12, which would give us negative 23, I think, which is not greater than 0. So that doesn't work. So we do have it right. So it should be from negative infinity up to 2, square brackets, union, square brackets, 6 to positive infinity. And that's it. So generally factoring one's pretty straightforward. Factor them, get your two factors, test either side. So I got one more example here. Let's try this one quick. So it's almost the same, just a little bit tougher to factor. So remember, when you have that number in front, you have to factor that out accordingly. So we'd have 2x and 1x would be our two factors for that one. 12, we're likely going to get 3 and 4, so let's just try that as a trial and error. So if we put 3 and 4 in, something like that, we know one of them has to be positive, one has to be negative. Let's guess positive there, negative there. Let's just quickly FOIL that out to make sure it works. 2x squared is good. We get minus 8x plus 3, which would give us the negative 5. So we're good. So from here, our two intervals should be at negative 3/2, right? Remember to divide by that negative 2. And then for the second one, we would get positive 4. So our number line will go negative 3/2 or negative 1.5 if you want to do it that way, up to positive 4. And again, if we look at our original question, it was just greater than, so they should be both open dots. And let's try a test point of 0. If we plug 0 in, we get 0 minus 12 is negative 12, greater than 0. It's not. So 0 would have been somewhere in the middle. So 0 doesn't work, so our intervals are going to go outwards once again. So for this one, we'd write our final answer as negative infinity to negative 3/2, round brackets, union 4 to positive infinity. And that's it. So we have our interval notation, quick review. We looked at doing rationals where you have to remember to do the non-permissible on the bottoms, keep that as one of your interval points. We looked at factoring, we looked at absolute values. The point, generally what the key thing is, just remembering how the intervals work, open circle, closed circle, and to remember, use some test points to help you figure out which directions they need to go. And that's all for today.